I'd like to thank the organizers for inviting me, giving me this opportunity to tell you about some of the work that we've been doing on primarily twisted trilayer graphene today. The work that I'll be talking about today was carried out by 𝗏𝗏, Andrew, and Zhu. Samples were made in Pablo's group, and we benefited from a lot of fruitful discussions with the group of 𝗏𝗏. So let me start with twisted bilayer graphene. These are inverse compressibility measurements, namely measurements that are primarily sensitive to many-body energy gaps in the system. And bright colors indicate gaps, and the bottom panel here is the distilled version of the measurements that you see above. And I think the kind of important message here is to realize that this system exhibits tremendous variety of phases that can be tuned into just by varying slightly density or magnetic field. And we've heard a lot about some of these phases already this morning, namely many of these phases correspond to spontaneous breaking of flavor symmetry, namely the bands here have spin and valley, and the system, for example, these correlated insulating states or the Chern insulator states, they have spontaneous breaking of flavor symmetry. This also includes the fractional Chern insulators here that have broken flavor symmetry, but no additional breaking of translational symmetry is needed in order to explain these states. But in addition to these flavor symmetry broken states, there are other states here that, in order to explain their appearance, require an additional breaking of translational symmetry. Namely, the system has to spontaneously enlarge its unit cell, for example, to produce what we'll call a symmetry-broken Chern insulator that has a fractional intercept at filling factor 2 2/3 and a Chern value of +1. In order to explain this state or these blue states here, which intercept at 3.5 and 3 2/3, an additional symmetry needs to break in the system spontaneously in this case, and that is additional translational symmetry. And the interesting thing here that actually goes beyond even conventional quantum Hall effect is that these phases compete with other phases like the fractional Chern insulator states in the system, and it's not yet entirely clear what governs this competition and which one would win under different conditions. So having this insight led us to consider an analogous system, and that's the twisted trilayer graphene system, which has precisely the same energy bands as the bilayer system, namely flat bands, but in addition, it has also a Dirac sector, which in principle should not couple to the flat bands. And we were, number one, curious to see to what extent the presence of these Dirac electrons will alter the physics that we see in the flat bands. There's an additional interesting property of twisted trilayer graphene where the top layer and the bottom layer are not twisted by exactly the same angle with respect to the middle layer. If they're not twisted exactly by the same angle, this leads to a large-scale, long-range super-Moiré scale, an additional potential landscape that now explicitly breaks translational symmetry. And we were curious to see, as opposed to the spontaneously broken translational symmetry states that we saw before, to what extent these states are going to be of interest and demonstrate the presence of strong interactions and topology. So here is a measurement of the inverse compressibility in one of the samples, the twisted trilayer graphene. And you can see again this kind of tremendously rich set of phases that emerge, but different from the twisted bilayer graphene, which will be the focus of this talk, is number one, the presence of these strong blue features. I don't have the scale here, but blue features correspond to negative compressibility and are in fact a signature of first-order phase transitions. So these occur within the charge neutrality sector, and I'll dive a little bit into that. And in addition is the appearance of these replicas that look like fractional intercepts, and these are a result of the explicit breaking of translational symmetry introduced by the super-Moiré, and I'll talk about what is the underlying characteristics of those features as well. So let's focus first on the 0th Landau level, namely charge neutrality. And here you can see very clearly these very strong negative features in compressibility signifying the breaking of translational, competition between the Dirac sector and the flat band sector. So one thing we can do, instead of plotting this plot in units of density and magnetic field, we can convert density to filling fraction. And note here that the filling fraction goes from -6 to 6 because the Dirac sector has a degeneracy of 4 and the flat band sector has a degeneracy of 8, so a total of 12 states going from -6 to +6. The action really happens between -6 and +2, so we'll focus only on that sector. So this is now Landau level filling factor and magnetic field, and you can see the vertical features here which correspond to the integer filling. And you see that these are interspersed by these negative compressibility signals where the gap closes and then reopens. And in order to understand what's going on here, one needs to realize that in each one of these Landau levels, so we're focused on the 0th Landau level of both the Dirac and the flat bands. So we have a total of 4 bands for the Dirac sector and 8, 4 of which are shown here for the flat bands. In order to explain the data that you just saw, one actually needs to introduce an offset between where the Dirac point for the Dirac electrons are and that of the flat band. And one needs to assume that each one of these spontaneously broken flavor symmetry here disperses with some slope and magnetic field that we call an effective G factor. Some of these states are true spin states, so they would be really G factors, but some of them are valley states, so they would be some effective dispersion of these energy levels with magnetic field. And you see that the offset and the linear dispersion leads to these crossings that are responsible for the phase transitions. I don't have time to explain in great detail, but if one ignores the interaction between the two flavors, one would not be able to explain the appearance of these phase transitions that occur away from the integer filling. They would only occur at integer filling. So by introducing an interaction term that weighs the competition between putting an electron on the same species, let's say Dirac electron or flat bands versus one in the flat band and one in the Dirac sector, is responsible for giving these phase transitions. And I want to emphasize that these are very similar to Stoner phase transitions, namely, they really require that the system has finite density of states. And in fact, in order to get a good agreement, we need to assume that the density of states or the width of the bands of these Landau levels of the flat band are considerably broader than those of the Dirac sector. And this gives us a very nice agreement of where all these phase transitions would occur across the different phase diagram. The second topic that I mentioned that is very different from the twisted bilayer graphene is that of these replicas that you see here. One replica, a replica, a replica, and a replica. If you go all the way to high magnetic fields, we see that this spectrum actually consists of more than 40 new levels that are not present in the twisted bilayer graphene. And if you follow these slopes all the way down, you see that they intercept at a variety of intersections, predominantly at an offset of 0.3 in units of filling factor, but also 0.3/2 and 0.3/4. And this suggests that whatever is causing this spatial breaking of translational symmetry also has some interesting physics involving the flavors of the Super-Moire scale. So to see this a little bit in greater detail, let's focus on some of the filling factors that we have here. So as I mentioned, first of all, these states can be characterized not only by their integer intercept, namely whether it's a integer quantum Hall effect, symmetry broken Chern insulator, but also in terms of the Super-Moire, this extra length scale that breaks translational symmetry, and we can see that we have intercepts at integer breaking of that spatial symmetry, as I mentioned, 0.3 or 0.3/2 or 0.3/4, and I'll dive into this just now. So if one looks at the charge neutrality when one sees this replica, and I'm going to call this density the density needed to fill up the supermoire lattice. And here again, I'm just highlighting that all these Landau levels here intercept at filling factor 0.3 or 0.3/2 or 0.3/4. Interestingly, if one looks at this specific replica here, it has a degeneracy which is identical to the one near the neutrality point. This means that in order to fill this band, we need to fill 4 flavors of the supermoire lattice. But now we can ask, well, what happens at filling factor 2? So at filling factor 2, we see that there is a replica here, and if we zoom in, we see that that replica actually appears at a filling factor of the supermoire density over 2. Now this might not be that surprising because when we're at filling factor 2, we've already exhausted 2 flavors. They're completely filled, so the only remaining electrons that we can play with are the remaining 2 flavors. And so when we're filling up the supermoire band, we only have 2 flavors to fill before we reach a full band of the supermoire. Similarly, if we consider what happens, and this maybe we can see kind of in a zoom in here. Interestingly also, if you look at the degeneracy, the Landau level degeneracy of the main moire band and that of the supermoire, both reveal a 2-fold degeneracy. So not only we know that this is the flavor symmetry is broken on the supermoire scale, which is much larger. It's about 30 to 40 nanometers length scale. We also see the Landau level degeneracy indicating a 2-fold degeneracy. Another thing to point out is that the incompressibility of the main moire scale and that of the supermoire scale are comparable. So the energy gaps that are being open both on the moire scale and on the supermoire scale are for some reason comparable. If we go further to filling factor 3, now we see that this density offset is supermoire over 4. And again, maybe not that surprising, because at filling factor 3, we've exhausted 3 flavors out of 4. Namely, we have only 1 flavor left to play with, and that is the flavor that is being used to fill up the supermoire band. Looking at the Landau level degeneracy of this supermoire, again, we see a single 1-fold degeneracy, indicating again that we have full flavor symmetry breaking on the supermoire lattice, and again, incompressibility comparable to the moire and the supermoire. So somehow interactions on the supermoire scale are as strong as those on the moire scale. Perhaps the most surprising element here, after I've convinced you that we should expect flavor symmetry on the supermoire scale, is what happens at filling factor -2. So filling factor -2 also has flavor symmetry breaking, namely 2 flavors completely filled, only 2 flavors left to play with, and yet in order to fill the supermoire bands, we need a full 4-fold symmetry. So something in the -2 near the hole side here restores flavor symmetry once we move away from filling factor -2, and this remains a puzzle. We're suspicious that this might be related to the appearance of superconductivity on the hole side, but it's still something that we need to understand. Again, magnitude of incompressibility is comparable to the moire scale. The features that we're seeing are very robust. This is a spatial map as a function of position, roughly 6 microns, and you can see where these replicas appear. They're meandering around very much like the moire itself, from which we can then extract what the moire twist angle is, the supermoire wavelength, and you see that it's kind of wandering around from 30 to 35 or 40 nanometers, and we can extract the degeneracy. And you see that that is very robust. Filling factor 3 has a single-fold supermoire degeneracy, as we expect. Filling factor 2 has a 2-fold, and filling factor -2 has a degeneracy of 4, which is the puzzle. We don't have an explanation for that, but we could generate some of the features that we see again by introducing a simple model that takes into account new types of electrons in the system, namely the 𝗲 electrons and the super-𝗲 electrons. That gives rise to additional density of states at the super-𝗲 band filling. And when you look at the incompressibility predicted by a simple model, you see that for comparable interaction between electrons sitting on the super-𝗲 and the 𝗲, you can get double peaks, as we're seeing in experiment. But you see that the range of parameters that produce this is narrow, and for some reason, this is the range of parameters that the system has chosen. So with this, let me just summarize. The twisted trilayer system is quite different from the monolayer. Number one, in terms of the competition between the Dirac sector and the flat band sector, giving rise to many Stoner-like transitions between the different flavors of electrons. And second, it allows us to explore the presence of explicit breaking of translational symmetry that produces these kind of fractional filled states at the super-𝗲 scale, and the interaction scale for those features are comparable to the 𝗲 scale, something that we don't entirely understand, and the puzzle of what is going on at filling factor -2, where fourfold symmetry has been restored. And with this, I'll stop and take some questions.
Hey, questions? Yeah, right at the bottom. Oops. Okay, after that. Yeah, go ahead.
Thank you for your talk. I have one question. So you've shown that at filling factor -2, that the generosity is not the same as +2. What about then -1, -3 as compared to +1 and +3?
So unfortunately, in this sample, we don't see energy gaps at -1 and -3. We only see the -2. So I cannot answer that because the sample is just not showing us the gaps
I
there.
see. Okay, thank you.
Okay, over there. Yeah.
Hey, Amir, just doing my job. I'm curious, the Dirac band versus the flat band, do they live, I forget now, do they live in different parts of the layer? And could the reason for these differences be happening because there's internal polarization of the charge within the three layers, something that happens in, let's say, ABA graphene as well? Could that be a reason?
Yes, so they don't live exactly one on top of the other. In fact, if the system has perfect mirror symmetry, then the Dirac sector is completely decoupled from the flat band sector. Now, once you're starting to change the density in the system, obviously you're introducing a displacement field which breaks the mirror symmetry and couples the two. And I didn't have time to talk about this, but you can see that these incompressible features, they kind of stop going along a straight line and they break down at low magnetic fields. This also has to do with the competition between the Dirac and flat band electrons. And so they get mixed up, and in particular, near the charge neutrality, where I mentioned these Stoner-type transitions, there the system has enough time to figure out where its minimum energy is and arrange itself in the lowest energy configuration. Here, in fact, what's happening is the Dirac electrons are, in fact, compressible, and the flat band electrons are incompressible, and yet they coexist one with the other.
Yeah.
Instead of a Dirac cone, if you have a parabolic band, in that case, would you expect a different magnitude of super-𝗲 interaction compared to what you observe with the Dirac cone?
So you're asking if we had maybe a 4-layer system and...
Yes, exactly.
It's a good question. I don't know. I think, number one, there are going to be more ways of creating a super-𝗲 scale. You have three angles that you can play with and not just two. So I don't know. It's a great question.
Thank you.
Right, any other question? Okay, I have one small quick question. So suppose you have a bilayer graphene or some, and then have boron nitride on the two other sides and create a super-𝗲 from aligning the angles from. Will you get the same physics over there? That's another way of creating the supermoire.
Probably you would have, yes, I would imagine you'd have, so if you had a twist angle between the two layers of graphene that gives you one length scale,
Right.
and then you have some alignment, let's say of HBN, you will then get another length scale. We have samples that we've studied there. What we typically see when you align the twisted graphene to HBN on one side is predominantly just breaking of C2 symmetry. We don't see indications of supermoire.